Okay, so very good afternoon and Shubho Bija and happy Dussehra to all of you. I hope all of you had a very good Durga Puja vacation and now it's time to get back to work. So we were discussing memory hierarchy in computer design, and we saw that ideally uh, the memory hierarchy is based on the primary observation that there is a principle of locality. There is a temporal locality and a spatial locality principle, which are very fortunate features of the type of programs or the data usage of programs that we typically run on our computers, which allows us to only work with a small subset of the entire program body or the data that it works with at a given point of time. Later on, you might require other parts of the program or other parts of the data, but at any given point of time, your usual access is limited to a relatively small portion in a neighborhood. Based on this principle and the observation that it is relatively inexpensive to have large but slow memory in the form of, say, hard disks, but it is relatively expensive to have fast memory in the form of SRAM or DRAM. We have built a hierarchy where you have everything at the lowest level in the hierarchy, and based on the need of access, when you need just in time, you bring the necessary information from the lower level of hierarchy up to the next higher level, then up to the next higher level, then up to the next higher level, in this way up to the registers of the processor where they get executed. In the processor, please understand, cannot execute stuff which is in main memory, that which is usually DRAM in our computers. The processor needs the necessary instructions and the data that is accessed by the instructions to be in its registers to operate on them. And these registers are inbuilt inside the processors, very fast, directly clock driven, driven by the same clock that drives the processor. So they are very fast, very efficient, but of course the flip-flop design of flip-flops takes relatively more and they are very power hungry. So you have a number of registered in the processors, that is impossible. So you have only a fixed number of registers, and as and when you need, you bring data from the lower levels up to the processor to process. There are some concepts called hit ratio and miss ratio. When the processor searches in the level hierarchy, memory hierarchy level closest to it, if it finds the data, it is called a hit. If it does not find the data, it is called a miss. Now, in the previous classes, we have discussed the static RAM, which is basically the technology with which cache memory is designed, which we have not yet discussed. Cache memory is a small memory different from the registers. This is also important to understand. The technology is different from registers. The operating principle is different from registers. The cache is as such not part of the instruction set architecture. Okay, the cache is something different. It is an inbuilt memory in the processor, no doubt, but it is different from the registers. Don't confuse between cache and processor registers. Today we will discuss cache memory. It is usually built using SRAM technology. Then the lower level of memory hierarchy is dynamic RAM or DRAM. It is made using again silicon technology, but slightly slower devices. However, the number of transistors necessary to build 1 bit of DRAM is usually 1 transistor per DRAM bit, whereas for a cache memory, it can be 8 transistor or 10 transistor, something like that. So cache memory is much more expensive. It is faster than DRAM, but it is more expensive, more power hungry, etc. At the lower level of hierarchy is the magnetic disk, which is slowly going out of use, and as I predicted in the last class, maybe within the next decade or so it will go completely out of use. But this type of prediction has been made by many people since the 1990s, that magnetic disk will go out of use. They are still very much a viable option. Many personal computers, laptops, and they have redundant days of magnetic which help in data backup and fault recovery. Okay, so we will probably not have time to go into it. That is also an interesting topic of how to build arrays of redundant disks to have fault tolerance in your database or the stored data. We will not go into that. So the ideal memory should have access time of SRAM and the capacity and cost of magnetic disk. That search for an ideal memory is still continuing. It has not yet finished. However, flash memory has become very common and has started replacing this magnetic disk. A flash memory is the prevalent type of memory that you see in smartphones, tabs, etc. Many high-end laptops, but magnetic disks are also there. So DRAM, we discussed a little bit of DRAM, some innovations of DRAM design which can increase the throughput of DRAMs. One fundamental aspect of the DRAM is that the clock speed is not the same as the processor clock speed. It is usually slower. What is the clock speed will be usually mentioned in the specification of the DRAM. Modern DRAMs are often of the size of 8 GB or so, normal ones, and then you can have multiple of them on a motherboard. Say you can have 4 of them, 4 8 GB chips on your motherboard in 4 slots. Of course, your motherboard needs to support them using slots where you can just plug in these memory chips, and then you can have 32 GB of main memory. So by memory, by the term memory, we usually mean DRAM. Okay. Now, how the sizes of increase, etc. Some information is there. How to increase memory bandwidth. Different organizations of DRAM have been discussed. Now flash memory is becoming very popular. It has its own issues, that it is prone to degradation and finally failure beyond a certain number of read-write cycles. So they cannot have infinite lifetime, but because the integration density is very high and they consume much less power than magnetic hard drives, they are becoming very popular. Their cost is also decreasing. Finally, we discuss the classic magnetic hard disk drive. This is an extremely complicated electromechanical device. Why is it extremely complicated? Because the protocols that are used to read and write data on this are so complex, and the protocols that are used to interact with them from the main computer are so complex that they require full-fledged processors. Okay. So we have discussed that they basically are treated as they're essentially treated as IO type devices. Okay, and there is an interrupt mechanism by which they are accessed. Did we discuss the interrupt mechanism and other things, students? Hello? Hello, are you there?
Yes, sir.
Yes, sir.
Yeah, so interrupts, etc. I started teaching. How much was covered? in the last class before we stopped? Do you remember?
No, sir.
So I think we got till the interrupt table.
Huh?
So the interrupt table, interrupt
vector table we covered. Okay, okay. Yeah, I think we discussed. I think we discussed interrupt vector table. Yeah, I think direct memory access. Did we discuss DMA?
So we started that.
Okay, fine. We will discuss it. Continue to discuss it maybe in tomorrow's class. Let us first get done with this, or maybe on Thursday's class. Let us first get done with this memory hierarchy. Then again, maybe we will come back because the attendance of that day was very, very low. So maybe I will reteach some of the concepts of that day. Anyways, yeah. So this is usually combined in several magnetic disks. Data on these magnetic disks are written on both sides of the disk, and they are arranged in something called tracks, which are circular bodies of this collection of data. The data is further organized in each track in terms of small modules called sectors. Every sector contains some data along with some additional auxiliary information which identifies the sector, that is the sector ID, some error recovery code, etc. Combination of the sectors, combination of the tracks at the same radius from the center, okay, is called a cylinder. This is an imaginary concept, but the importance of this concept is that all the sectors that are under the read-write heads in the on the same cylinder, okay, can be read at the same time. Now, read-write heads only perform movements towards the center or away from the center. They cannot perform rotation. The rotation is actually performed by the disks, and depending on the current location of the read-write head and the current location of the starting point of the data or the next starting point of the next piece of data, the read-write head needs to move, plus the disks need to rotate so that the starting point comes under the read-write head. These two accesses are the latency of this is not predictable at priori, because where my data will be located is not predictable at priori. That is why the dynamic, this magnetic disk cannot be classified as a dynamic access memory. Okay, dynamic, sorry, as a random access memory, because in a random access memory, by definition, the time necessary to access any data at any address is constant. Here, unfortunately, that is not the case. There are several delays associated with this memory hard disk. We saw some of them. There is a queuing delay. What is the queuing delay associated with the memory hard disk? Well, several processes might be waiting to access the memory hard disk. I discussed this in the class that we had earlier. There can be a seek delay because of the head moving. There can be a rotational latency, data transfer latency, controller overhead, etc., etc. Okay, so this type of calculations are possible to do. Now, notice that disk drives themselves can contain some cache, some inbuilt memory, where they can prefetch some sectors in anticipation of being accessed. Okay, and so that as soon as the process requests that, it is immediately ready with the data. Says, yeah, it is available. I don't need to read it further from my disks. Please take it. Okay, so all this intelligent stuff is controlled by a full processor type complexity chip, which is built inside the hard disk drives. Okay, the two protocols that are common are, one is advanced technology attachment and its version serial advanced technology attachment or SATA. That is the type of hard disk drive that you probably have on your desktop or PC if you are at all having a hard disk drive. However, there is another option called SCSI, Small Computer System Interface. Although it is called Small Computer System Interface, it is actually more common in computers which use which perform large volume of data transfers, for example, in data warehouses and so on. Now, finally, we come to cache memory, okay, which is the most interesting type of memory that we will discuss. What is cache memory? By cache memory, we generally mean a small semiconductor memory that is built inside the processor itself. Okay. This is a relative understand that this cache memory in processors that were built, say, 1990s. Okay. On-chip cache, on-chip microprocessor cache is a relatively new technology, probably less than 30. Why it is a relatively new technology? Because it is difficult. It was difficult to, given the large relatively large transistor dimensions earlier, to fit so much of memory on the same chip and to keep the chip size to a minimum. Also, the cache consume a lot of power, etc. Okay. So based on all these things, it was difficult. However, as time has gone by, in the modern microprocessors, if you look at there is something called a microphotograph of microprocessors. Okay. So if you look at them, let me see if I can find them. Not finding very good photographs, but anyways, you just search for say i7 micro photograph or something on Google, and you will find that large portion of the chip is actually occupied by the cache. There are multiple cores. In each core, the individual cores have private caches. Okay, that also is at least 50% or 60% of the area. Plus, in the entire cache. So cache memory itself, there is a key applied and the hierarchy is applied to have multiple levels. Okay. So the entire chip, if you calculate, maybe 90% of the total area is occupied just by the cache memory. And the actual arithmetic logic unit, the floating point unit, the other parts of the pipeline which we will study later on, all of these actually occupy maybe 10% of the area, which is quite surprising actually. That memory inside a microprocessor is actually occupying the maximum area. Anyways, that is the way the trend is moving. Typical sizes of this cache, nowadays there are 3 levels of cache, usually in the most cutting edge modern chips. The largest L3 level typically is in the order of tens of megabytes, so 10 or 12 megabyte on a good chip. At the lower levels, L2 level, maybe it is single megabyte or maybe maybe say 5-6 megabytes, etc. And at a further lower level, maybe it is in the order of some kilobytes or so. Okay, so in this way it is kind of further arranged. Anyways, in our discussion in this course, to make life simple, we will keep ourselves confined to only one level of cache. Okay, so as if there is only one level of cache in the processor. That is what we will consider to keep things simple. Later on, if you take more advanced computer architecture courses like HPCA, you will be taught issues, design of microprocessors which have multiple levels of cache and what are the issues associated with that. Multiple levels of cache is helpful, but they also create other problems, and how those problems are solved, etc. There is a problem called cache coherence and how cache coherence is resolved, etc. All these things we will study. Anyways, so cache memory is the level of memory closest to CPU. The fundamental problem that we need to answer is that I will be given a sequence of read or write accesses in terms of memory addresses. These x1, x2, x3 up to xn, these are addresses. Okay. Remember, these are basically starting addresses of words, you can say, keep things simple, or some byte addresses. Okay, just some byte addresses. If it is a starting address of a word, usually it will be a multiple of 4. I mean, to keep things simple, we can consider that maybe they are multiples of 4. The question is, there are two types of operations. One is a read operation and the other is a write operation. For read operation, first of all, the addresses that are generated by the program, those are memory addresses. Now the microprocessor is not directly connected to the memory, it is connected to memory through the cache. The cache memory is sitting between the microprocessor and the memory in a way. The cache memory is located on the microprocessor, no doubt, but it is kind of in between the memory and the microprocessor. The microprocessor cannot directly see the memory. This is the problem. So given this address, we first need to look inside the cache. Is it here? Okay, where to look? Because the address that was given to me was a memory address, but I must now look inside the cache, which is much smaller than memory. And if at all I can calculate where to look for it, how do we know that I can trust the data that I am finding there? Because data might be present from some memory can, uninitialized memory can contain data. How do I know that data is trustable? Because again, I am not directly looking at the memory. My direct access to memory has been stopped now. In between, some cache is sitting there. These are the questions which have to be answered for read type operations. Second is for write type operations. Again, where do we look for it? I want to write at some certain memory location. Okay. Till now, when you have written assembly language code, you have just written SW and writing has happened. You have just written LW and reading has happened, etc. Now you will still write LW and SW instructions, but those addresses will now be internally analyzed to check whether the data that you want to load in your register using LW instruction, is it already present in the cache? Where to find in the cache and whether I can trust the data that is there, or I need to get it from the memory to the cache. Means there will be a cache miss and I want to get the memory, I have to get the data from the memory to the cache. Secondly, when you are executing an SW instruction, there is an address, but now the processor cannot directly look at that address in the memory. So it must first look at some corresponding address, correct location inside the cache. Inside the cache, where to look for it? Okay, I cannot look at the entire cache. I mean, that might take too much time because the cache itself can be quite large, as we will see. And the second complication with write is if the data is in the cache, I find that yes, this is the location where I have to write the data. Is the data in the cache sync to main memory means the value that is present in the cache currently, has it been synced to main memory? Because otherwise I will just overwrite the data and there can be implications. If it is a shared data between two different processes, then somehow I need to inform the other process that the value that you find in memory is not synced to the value that is I am going to now that is there in the cache, and that value is again going to be updated. All these complications come. So the handling the write operation is actually more complicated than handling the read operation, and handling the write operation we will study in tomorrow's class. First, let us start with a relatively simple scenario of handling how to handle the read operations. Means how to look for where to look in the cache if I given a particular memory address, and whether you can trust the data in the cache. These two must be answered. First, one fundamental issue with cache is that its size is much smaller than main memory. This is true in all caches. Even if you consider a modern L3 level cache, okay, that cache is say in a very good processor, it is say 12 megabyte, 16 megabyte, 32 megabyte. What is 32 megabyte in comparison to your main memory, which can be 32 gigabyte? Okay. So there is a factor of 3 shrinkage in size of the cache memory with the main memory. So that is you have to be very particular about what to have in the cache. Otherwise, you have to be very prudent and very wise about what to have in the cache, because you only have like 0.1% of what you have in your main memory in the cache at any point of time. So those are very precious resources that you have in the cache. Okay. If the microprocessor finds the data in the cache, then there is no miss. So everything gets satisfied. The entire load store operation would happen in one clock cycle. If it does not find the data in the cache, there will be a cache miss, and then it needs to go to the main memory to fetch the data, and then the latency can be as bad as 100 clock cycles. Okay, hundreds of clock cycles. So you have to be very prudent. Now, so because the cache is much smaller than the main memory, I must find a mapping mechanism of the addresses from the main memory to the cache memory. Okay. Now, when we talk of caches, we usually talk of something called blocks. What is a block? A block is a unit of data or instructions, I mean a chunk of data or instructions which the cache handles at one go. Okay. Block, or sometimes it is called line. I think cache line is also the what I personally like a bit. I prefer the term block, because the cache line somehow gives an idea that as if it is some electrical line or something, electrical connection. It's not like that. Now, what is the size of this block? Well, that it depends on the cache design. The block size can be a single word in your MIPS 32, that means 4 bytes, or it can be multiple words. Typically, in modern caches, the block sizes are multiple words. In real life caches, there is no point making a block as small as one word. Okay, because once you are accessing data from memory, it is better you access larger amounts. Okay, that is the philosophy. but there is also another catch. You should not make the block size too large. We will come to that. There should be a balance between the block size lower limit and the upper limit, something like that. The first type of cache organization that we study is called a direct mapped cache. This is a very simple cache. How do I map the address of the block in memory to the block in the cache? Well, now you also think of the addresses in memory in terms of blocks. Okay, later on we will see how to resolve this, because addresses usually would not be given to me in terms of blocks. They would probably be given to me in terms of byte addresses or word addresses. And how to do the mapping from byte to block address and then further to the cache block address, we will see very soon. But for now, assume that in the memory also, these addresses that are given, this 0, 1, or these all these things, these are actually, you assume, these are block addresses. Okay, so as if they are multiple word hypothetical blocks. Okay. Now, in the cache that is given here, there are only 8 blocks. Whereas, in the memory that is given here, there are much more. There are probably 32 blocks or so. How do I map a block address in memory to a block address in cache? I take the block address in memory and I calculate a modulo the number of blocks in the cache. In this cache there are 8 blocks, so I calculate modulo 8. Okay. What that means is that I can just, because the block size, number of blocks is usually a power of 2, like 8, 16, 32, etc. I can just look at the last 3 bits. Okay. I mean, just the lower order address bits and at the memory block addresses, and put them to the correct cache locations. For example, if there are so this is an 8 block cache, which means I need to look at the last 3 bits in the memory block address. So I said I look at all the memory block addresses which end with 001, the ones which are shaded in gray. Okay, so it can be 0001, then 01001, etc., etc. Now all of them will map to the same cache block whose index, this is the block number in a cache, is called the index. Okay, very soon we will see another diagram which will make it clear. All of them map together to the cache block index. Okay, so this is like this is the way it performs a many to one mapping of memory blocks to the cache. Now, can I ask you a question? Looking at this, it is clear that finding the cache block where I should look for the memory block is very simple. It is not at all difficult, and it is not at all difficult. Now, my question to you is, what is the problem with this? Can you see any problem with this organization? What problem can you see with this organization?
So for one block in cache, there are 4 blocks in memory.
Yeah, so what, yes, very good. So what problem does this create?
So we didn't find the output which we wanted. The problem remains the same, but it just got shrunk.
Yes, so the problem is that multiple blocks in memory are fighting for a single block resource in the cache. So that is the problem. So if one, currently I have, say, the block number, so my address is such that I am basically looking for a particular word which is located inside block number 00001 inside main memory, and that is mapped to block 001 in the cache. Okay, fine. And it also assume that currently it is not in the cache. So when I first perform a LW instruction, the cache mechanism, it is completely circuit controlled. The hardware mechanism says there is a miss. So if there is a miss, in that case, that block is brought from memory to the cache. That there is a 100 cycle penalty for this. Okay. Now, in the very next instruction, there is an LW which requires the data which is located at memory block address 10001. Okay. Then again the cache hardware mechanism says, well, I don't have the data corresponding to 10001. Okay. I must fetch it from main memory to the cache, but where will it come and sit in the cache? It will come and sit in the cache where currently the content of block number 00001 is from memory is sitting, right? So it will come and overwrite the block that you had just now brought from main memory to the cache by spending 100 clock cycles. So it's a huge wastage of effort, and this 10001 block will come, overwrite the stuff in the cache. Okay, so there is a lot of conflict. So in the organization shown here, 4 blocks in main memory at a time are fighting against each other for the same resource on the cache. Situation in real caches is worse, because as I told you here, to make things simple, they have shown that as if the cache size is only 1/4 of the memory size. Okay, situation is quite bad in real life caches. In real life caches, the cache is 0.1%, less than 1% definitely. Okay, from the main memory, which means 100 blocks are fighting for the same cache block. Just imagine, okay, 100 blocks in memory are fighting for one single cache block. So consider a very crowded train or bus. All of you probably have been in very crowded trains or buses. In a peak hours, rush hours, there are only, say, 50 seats in a train compartment, and 200 people are fighting for they are in the compartment. Only 3 of them are standing, 1 person is sitting. Okay, when 1 person gets up, only 1 will be able to sit there, remaining will keep standing. Okay, so this is the situation in direct map cache. It is quite simple to understand and to design, but it is not efficient. Now, further questions have to be answered. Looking at the organization given here, can you tell me how do I know whether at any given point of, so suppose I have a LW instruction. So I first look in the cache. From the address, it is that was there in the LW instruction. It is clear that I should look at indexes 001. I go to index 001 and there is some data present there. How do I know that this data is for 00001 or 01001 or 10001 or 11001? How do I know that? Any answer, any suggestion? So we have, so there were two questions, remember. Where to look for the data and how can I trust the data? How do I know that this is the actual data I am looking for? First part we have answered by a simple mechanism of taking a modulo with the number of blocks in cache, and since the number of blocks in cache is usually a power of 2, I just look at certain number of bits depending on the number of blocks in the cache of the block address for which I am looking for, and I go at the correct cache location. This much is done. The second part is how do I trust the data? How do I know that this is the actual data? Any suggestion? How do I know see the complete memory block address is 00001 or 01001. I only have got partial information that okay, I have reached 00001 in the cache, but all four are mapped to the same, right? Which exactly is present? How do I know?
You need to store it somewhere, like what?
Yeah,
is
right.
there.
Very good. Very simple solution. The additional information of the one that is actually stored currently in 00001 location in the cache, that additional information, which in this case is 2 more bits of address information, that has to be stored somewhere. Where somewhere will you store it? Well, you store it in the cache itself. This portion of the higher order address bits, okay, is called the tag. The tag combined with the index uniquely identifies the address. The tag itself has to be stored in the cache somewhere. Now another additional problem comes. So the organization is something like this. So to make life simple, they have assumed the block size to be 1 word. Okay. And assume there are 1024 blocks in cache. That is, the cache size is 1024 words because every block is 1 word. This is a very simplistic assumption. Okay, this doesn't occur in real life. Most blocks will be more than 1 word in size. Here, to make life simple and to let us work with purely word addresses instead of block addresses, we are giving this example. Otherwise, please understand that you will need to work with block addresses. Now, given a 32-bit address, the last 2 bits are byte offset, which are basically word offset. We have already seen that the last 2 bits we do not consider. Now, because there is 1 word, okay, because that is the block size. Then the next 10 bits in this case are indexed. Why there are next 10 bits are indexed? Because that occupies the that 10 is dependent on the number of entries in the cache. So how many blocks were there in the cache? There were 10 blocks in the cache. Sorry, 2 power 10 blocks in the cache. 1024. So 10 bits are used for the index. Okay, so as soon as you get an address, you leave out the last 2 bits, the last 2 LS bits. Then you look at the next 10 bits from bit location, address bit location 2 to address index 11. look at these 10 bits. Immediately index to the correct location in the cache. Okay. Now, after you have indexed to the correct location in the cache, my tag of the remaining address bits, which uniquely identifies the complete address, is the remaining 20 bits, because the complete address is 32 bits. So that 20 bit has to be stored in the cache. Storing 20 bits is not like it takes a lot of area, a lot of memory, right? Because there are 1024 such entries. But you store 20 index of the location in the cache. You now match the tag that with is that you expect. Okay, the tag that you are looking for. If there is a match, okay, a 20-bit comparator is present. That equal to symbol shows a 20-bit comparator. If there is a match, exact match, it says yes, there is a hit. Okay, the comparator says comparison has succeeded. However, another complication arises. The point is, this is an SRAM type memory, okay? It can happen that just by chance, the tag just coincidentally matches the tag that you are looking for. But it is not the actual tag. I mean, it is the actual tag, but the data is not the actual data. Some junk uninitialized data is present in the data location in the cache entry, and the tag has just coincidentally, the 20-bit value string has just coincidentally matched the exact 20-bit string that you are looking for in the address. In that case, if you say, yeah, I have found the data and return the data from the cache to the processor, that is an error actually. To detect this scenario, another additional bit is maintained. This additional bit is called a valid bit. If the valid bit is 1, that means yes, this is an entry of the cache which is trustable. Initially, in an uninitialized cache, at the beginning of operation, all valid bits are 0. However, as you keep updating the cache and you write data into the cache in the locations, the corresponding valid bits are made 1. So now, after the comparator has returned true, you also logically AND it with the valid bit. The comparator says success and the valid bit is 1. That overall cache hit signal, if it is 1, that means it is a hit. It is 0, that means it is a miss. Even if the tag has matched, it is a miss if the valid bit is 0. This entire mechanism is hardware controlled. The hit miss mechanism is hardware controlled, and there are detectors for this hit miss mechanism and how to handle further. That is hardware control. Okay. If the hit happens, the searching for the data in the proper cache location and return of the data to the microprocessor, it can happen in 1 clock cycle, inside 1 clock cycle. So things are very fast. Searching the cache in a direct map cache is really easy. There is no search required, because in constant time you can just look at the index and go to the correct cache location, just depending on the index value. There is no search is required in the cache. Only some further comparisons are required of the necessary number of tag bits and the valid bit. Okay, and then you get the data. Now let's see a numerical example of what happens. Suppose this is a toy cache. This is much simpler than what we just saw. Why simpler? Because this is just a small cache with only 8 blocks. And again, there is a simplistic assumption that there is only 1 word per block. This assumption is not valid for most common caches. Okay, again I am repeating, don't assume that word and block are the same. They are different concepts. When you are dealing with cache memory, you deal with blocks. However, if I assume it is one word per block, that gives me a liberty of directly using the word addresses in my calculations, and that is what we are going to do. This is a 8 block cache, one word per block, direct map cache. Initial state, 8 indexes are shown, indices are shown, all the valid bits are initialized to 0. So that's why it is valid, showing no, n. Okay, that is, I mean, numerically it is 0. When it becomes valid, it will become y, that is numerically it will become 1. Now, and it is looking for address is 20, the same as a block address in this case. Okay, again, I am repeating, word address and block address in this example are the same. It will not be the case in all examples. Okay, so word address is 22 in binary, that is 10110. Okay, it is a miss because that data was not present. Okay, the index is 110. It is a miss because the valid bit was non-zero. But the first time it is in the LW instruction or something looks for it, there is a miss. Okay, this is a kind of a mandatory miss. Okay, and the cache block is 110 because that is the last 3 bits of the address. Notice how they have separated the binary address in the upper 2 bits and the lower 3 bits to show in the lower 3 bits show that there are 8 blocks in the cache. Okay, so there is a miss, but now the memory content of memory location 10110 comes and sits inside the data portion of the cache entry. Now every cache entry consists of one valid bit, necessary number of tag bits, and the entire data. Okay, please remember that. So every cache entry is not only the data entry. The cache entry is every row. The index is not need to be stored explicitly, but the remaining, the valid tag and the data portion, they have to be stored explicitly. So you need to calculate what is the cache size. We will see some calculations later on of what is the cache size for different organizations. Now the valid bit is turned to y. Why? Because the data was actually brought from memory to the cache. Okay. The next address it searches for is 26. In binary, that is 11010. So it goes to the index 010. Of course, it is a mandatory miss because nothing was present there. The valid bit was no. And the cache block is 010. The memory content 10 of block 11010 comes and sits in the data portion. The next search is again for 22 and 26. Now this time, because both were present in the correct locations in the cache, both are hits. Okay. So immediately the microprocessor is happy. In the first case there was a miss, second case there was a miss, but the next two, there were both hits. Now then 3 more come. First is 16, whose index is 000. It was not present, so it is a miss. The next is 3, whose index is 011. It was not present, so it is a miss. But when a miss happens, of course, you update the cache to store the content from memory. And then finally, the search is again for 16, but this time 16 was present. So there is a hit. Now, now the next one is for word address 18. The index is 010 because the binary of 18 is 10010. Well, the 010, the problem is currently if you look at 010, the tag is 11. However, for 18, the tag is 10. So although the valid bit is y, the tag is not matching this time. So this time, this is called a capacity miss. Okay, the cache has issues with the capacity of it. The first one were mandatory misses. Nothing, no mandatory miss can be prevented in any cache. Okay. Mandatory miss means the cache miss that happens when the first time the data is brought from the memory to the cache. Nobody can prevent that. But later on, whether miss would happen or not depends on the access sequence of addresses. Here, this is an example where now the conflict has happened between 16 and 18 addresses. 18 comes and kicks away 16, and it occupies. Although the tag valid bit was Y, still there is a conflict and it kicks out 16. Sorry, this is called a conflict miss probably. Yeah. Now, so memory address 18 comes and sits. So overall, how many misses and hits were there? 1 miss, 2 misses, 4 misses, 3 hits, 5 misses and 3 hits. Of which there were several in which nothing could have been done. That is true. The initial mandatory misses, nobody could have done anything. But the remaining, probably we could have done something better, as we will see in the tomorrow's class. Okay. So again, remember this diagram on slide number 26. This diagram, if you understand direct map caches. The only simplification in this diagram is here directly word addresses are getting used instead of block addresses. That is not the case in real caches. What is the situation in real caches? We will study, means how do we translate block address from word address to block address and then proceed. That we will study in tomorrow's class. Thank you.